Have you ever wondered what's really happening when you tap a number on your screen? You see a 5, but your phone sees something totally different, something that looks more like a series of light switches flicking on and off. So how in the world do we talk to our devices? Well, it turns out we have to learn their language. And today, we're going to pull back the curtain and decode the hidden number systems that power our entire digital world. Okay, so check this out. This really gets to the heart of it. On the left, you see the number 18. We all get that. It's simple. But on the right, that's how a computer sees the exact same value, 10010. To us, it looks like gibberish, right? So how do we bridge that communication gap? Well, the secret is actually way simpler than you think, and it's hidden in a system you already use every single day. So to learn computer is, we're first going to take a closer look at a language we already speak fluently, our own decimal system. Seriously, all the logic, every single rule you need to understand how computers count is hiding in plain sight in the numbers we use for everything, from buying a coffee to checking the time. We look at a number like this and we just get it, right? But let's really break it down. That 7 isn't just a 7, it's 7 times ones. The 2 isn't just a 2, it's 2 times tens. And the 4 is 4 times 100s. You see? A digit's real value comes from two things: what the symbol is and, this is the crucial part, where it's sitting in the number. Its position is everything. And this big idea actually has a name. It's called positional notation. And folks, this is it. This is the master key to everything we're talking about today. The idea that every single spot in a number represents a power of its base. For us, that base is 10. So we have the ones place, the tens place, the hundreds, and so on. Once you truly get this one concept, you can learn to speak any number language there is. All right, now that we've got the master key, let's use it to unlock those weird-sounding computer languages: binary, octal, and hexadecimal. Now, don't let the names scare you off. This isn't some kind of new complicated math. It's just different dialects that follow the exact same rule of positional notation. So here they are, the 4 main players. That word base just means how many symbols do you have to play with. We're used to base 10 because we've got 10 symbols, 0 through 9. Well, binary is just base 2. It only has 2 symbols, 0 and 1. Octal has 8, and hexadecimal has 16. And since we run out of numbers after 9, we just use the letters A through F for the values 10 through 15. Pretty clever, huh? So why do computers even bother with binary? Why just 2 symbols? Well, because deep down, a computer is just a massive collection of billions of microscopic switches. And a switch can only be in one of 2 states. It's either off, which we call a 0, or it's on, which we call a 1. So binary isn't some arbitrary choice, it's a direct reflection of how the hardware physically works. It's in their DNA. Now, the big problem is that even a pretty small number can turn into a super long, ugly string of ones and zeros. I mean, imagine trying to find a typo in that. It would be a nightmare for programmers. So we came up with a brilliant solution. We invented octal and hexadecimal. But here's the twist. They're not for the computer. Nope, they are for us. They're just convenient, human-friendly shorthands to make that binary code easier to read and manage. Think of this table as our Rosetta Stone for numbers. Just look at the decimal number 10. We see 10. A computer sees 0110. In octal, it's represented as 12. And in hexadecimal, it's just the letter A. There are 4 completely different ways of writing the exact same quantity. It's all about what language you're speaking. Okay. Theory is great, but now for the really fun part. How do we actually translate between these languages? It's not magic, I promise. It's just some simple arithmetic. So let's walk through the 2 key methods you'll need to convert pretty much any number you want. Let's start with the most common translation job there is, taking one of our normal, everyday decimal numbers and turning it into binary that a computer can actually work with. And we'll use that same number from the very first slide to see how it's done. This little recipe is called the division method, and it's your go-to tool for converting from our decimal system to any other base. The process is super simple. You just keep dividing your number by the base you're aiming for, so in this case, 2, and you jot down the remainder each time. That's it. Your answer is just all those remainders you collected read backwards. Okay, let's do it. We're going to convert 18 to binary. All we have to do is keep dividing by 2 and keep an eye on those remainders. Ready? First up, 18 divided by 2. That goes in perfectly 9 times with a remainder of 0. Okay, let's hang on to that 0. Next, we take our result, 9, and divide that by 2. That gives us 4, with the remainder of 1. Now we take the 4. 4 divided by 2 is 2, with a remainder of 0. We're getting close. And for the last step, 2 divided by 2 is 1, with a remainder of 0. So now for the big reveal. We take that very last quotient, which is 1, and then read all our remainders from the bottom up. So that gives us 1, 0, 0, 1, 0. And there it is, 1, 0, 0, 1, 0, exactly the number we saw at the very beginning. So what about going the other way? How do we translate from computer speak back into our familiar decimal numbers? Well, for that, we use the positional power method. And this is where that master key concept, positional notation, comes right back into play. We just multiply each digit by its positional value and add it all together. Let's try it with the binary number 11101. What on earth is that in our language? Well, remember, each position is a power of 2. So starting from the right, we have the 1's place, the 2's place, the 4's place, the 8's, and the 16's. We just add up the values for every position that has a 1. So that's 16 plus 8 plus 4 plus 1. And that gives us 29. Simple as that. Okay, you've got the basics down. But now, I'm going to let you in on a little secret. A pro tip that developers use all the time to quickly jump between hexadecimal and octal. It's a really clever shortcut, and it's called the binary bridge. Here's the magic behind it. So 16 is 2 to the power of 4, right? That means every one hexadecimal digit matches up perfectly with 4 binary digits. And 8 is 2 to the power of 3, so every one octal digit matches up with 3 binary digits. This clean mathematical relationship means we can use binary as a simple bridge to hop from hex to octal without ever having to convert to decimal first. So let's give it a try with the hex number 1AC. Step 1, we just swap out each hex digit for its 4-bit binary code. So 1 becomes 0001, A becomes 1010, and C becomes 1100. Then we just smush them all together into one long binary string. This is our bridge. Okay, now we're going to cross that bridge. We take that same long string of 1s and 0s, and starting from the right, we just regroup it into chunks of 3. Now we translate each of those little 3-bit chunks into its octal version. 100 is 4, 110 is 5, 110 is 6, and 000 is 0. And would you look at that? Our final answer is 654 in octal. A beautifully simple shortcut, right? So, when you really think about it, understanding these different number systems isn't just about math. It's about translation. It's about communication. We invented all these clever languages so we could give very specific, very precise instructions to our machines. And that kind of leaves us with one final big question. As these machines get smarter and smarter, what kind of language will they invent to communicate their complex ideas back to us?